Welcome to our latest video, which has the title More About the Equilibrium Constant Kc. This video is suitable for A-level students. By the end of this video lesson, you should have an improved understanding of the concept of the equilibrium constant Kc and what the values of this constant tell us about the position of an equilibrium. You should also be able to calculate Kc from given equilibrium concentrations and be able to work out the units for this constant. Now, in our previous video, we introduced the concept of the equilibrium constant Kc, and we also attempted some past paper questions where we had to calculate the value of Kc and work out the units for this constant. Now, the questions that we attempted in our previous video, where we had to work out the value of Kc and its units, were AS standard questions. So in this video, we're going to build on this and we're going to attempt some A2 level questions. Before we do this, it's important that we recap the meaning of the term Kc and what it tells us about a chemical equilibrium. Now, in our previous video, we discussed the fact that the position of equilibrium can lie to the right or to the left. And if the equilibrium lies to the right, we have more products compared to reactants. And if it lies to the left, more reactants. Now, the position of an equilibrium changes with temperature, pressure, and concentration. Now, we saw in our previous lesson that Le Chatelier's principle helps us deduce the effects of changing the temperature, concentration, and pressure on the position of an equilibrium. Now, the position of the equilibrium can be described by the value of an equilibrium constant, Kc, and the subscript C indicates that it's the ratio of concentrations that we're using to generate the value of this constant. So we're now going to look at how we express the equilibrium constant, Kc. So if we have an equilibrium A plus B going to product C plus D, Kc is equal to the concentration of the products over the concentration of the reactants, and the concentrations are raised to powers corresponding to the stoichiometry or the mole ratios in the chemical equation. Now, when writing the expression for Kc, we use square brackets to represent concentration. Now, the units of Kc can vary and it depends on the equilibrium, and Kc is derived from the concentration of substances. Therefore, it's valid for aqueous solutions and gases. However, we don't include solids when writing a Kc expression. Now, equilibrium constants can give us a guide to the degree that an equilibrium lies towards the products, i.e. the right-hand side, or reactants, the left-hand side. And an equilibrium mixture that has equal amounts of reactants and products would have a Kc equal to 1. Now, this is no surprise because Kc is essentially the concentration of the products over the concentration of the reactants. Now, if Kc has a large numerical value, then most of the reactants have been converted into products, and i.e. the equilibrium lies to the right-hand side. Now, if Kc has a value of less than 1, it means that there's more reactants compared to products in the equilibrium mixture, and the equilibrium lies to the left. Now, only a change in temperature can cause a change in the value of Kc. Now, although changes in pressure and concentration will cause the position of an equilibrium to shift, it doesn't affect the value of Kc. It's only temperature that affects the value of Kc. So we're now going to test what you can remember from our previous video about Kc with a quick practice question. So read through the question, pause the video, have a go at it, and then we'll go through the answers. So this question is all about the reaction of hydrogen and iodine to produce hydrogen iodide. And the first part of the question is asking you to write the expression for the equilibrium constant Kc. So Kc is equal to the concentration of hydrogen iodide raised to the power 2 over the concentration of H2 times the concentration of I2. Now to work out the value of the equilibrium Kc, all we have to do is substitute in the values that are shown in the question. So the concentration of hydrogen iodide is 1.71 times 10 to the minus 1. We have to square that, and we divide it by the concentration of hydrogen, which is 2.5 times 10 to the minus 2, and we times it by the concentration of iodine, which is also 2.5 times 10 to the minus 2. And if we do this, we get a value for Kc, which is equal to 46.786. Now we have to work out the units for this. Now we have two concentration terms on the top, so it's moles per decimeter cubed squared, divided by two concentration terms on the bottom, so it's moles per decimeter cubed squared. These cancel out, and therefore there are no units for the equilibrium constant Kc. Now that practice question was an AS standard practice question. Now at A level, the big difference with the calculations that you get is that the question may not give you all the equilibrium concentrations. In that case, you will need to work them out. Now a common situation is to give the concentrations of each reactant at the start of the reaction, and then give the concentration of one product at equilibrium. And there are a number of ways to work out the missing value or values, but one easy way is to use simple algebra, and that's the method I'm going to show you in this video. So to help us understand this method, we're going to do a worked example. So here's the sample question that we're going to look at. Now if an equimolar solution of A and B, where the concentration of each is 0.5 moles per decimeter cubed, is allowed to reach equilibrium, then the equilibrium mixture contains 0.2 moles per decimeter cubed of D. And the question says calculate the value of Kc. Now the chemical equation is given to you in the question, is A plus B goes to form 2C plus D. Now the way we go about solving this calculation is to first write down the initial concentrations of the reactants and products. So the initial concentration of A is given to you in the question, and I'm going to write down here initial concentration, and the question tells me that the initial concentration of A is 0.5 moles per decimeter cubed, and B is also 0.5 moles per decimeter cubed. Now at the start of this reaction we have no products forming, so the initial concentration of C and D will be 0. Now with this method we're going to let X be the number of moles that react. So because I have 1 mole of A reacting with 1 mole of B to form 2 moles of C and 1 mole of D, I'm going to write 0.5 minus X to represent the equilibrium concentration of A. And it's 1x because we have 1A in the equation. Now to represent the equilibrium concentration of B, I'm going to write down 0.5 minus x, and once again it's minus 1x because there's 1B in the chemical equation. Now to represent C at equilibrium, the concentration of C at equilibrium, we're going to write down 2x because there's 2 moles of C, and x is the number of moles that react, and x will be the number of moles that form. And for D, we're going to write down x because there's 1 mole of D in the equation. Now they tell us in the question that there's 0.2 moles per decimeter cubed of D at equilibrium. Now we've used x to represent the concentration of D at equilibrium, so therefore I can conclude that x is equal to 0.2. Now all I have to do now is work out the concentrations of A, B and C using x equals 0.2. So to work out the concentration of A, I have 0.5 minus 0.2, which is 0.3 moles per decimeter cubed. To work out the concentration B, I have 0.5 minus 0.2, it's once again 0.3 moles per decimeter cubed. To work out the concentration of C, I just do 2x, which is 2 times 0.2 moles per decimeter cubed, which is 0.4 moles per decimeter cubed. And the concentration of D has been given to me, 0.2 moles per decimeter cubed. Now to calculate Kc, I have to write the expression, which is Kc is equal to the concentration of C to the power 2 times the concentration of D over the concentration of A times the concentration of B. And then all I do then is substitute in these concentrations that I've worked out. So Kc is equal to 0.4, the concentration of C raised to the power 2, times the concentration of D, which is 0.2, divided by the concentration of A times the concentration of B. So it would be 0.3 times 0.3. Now if I put these values into my calculator, I get a value for Kc which is equal to 0.36. Now I have to work out the units, so I have 3 concentration terms on the top, as it's moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed, and I have 2 concentration terms on the bottom. So that means I'm able to cancel out 2 concentration terms on the top and the bottom. So that leaves me with units of moles per decimeter cubed. So my final answer is 0.36 moles per decimeter cubed. So now that we've worked through an example question, we're going to test your understanding with some practice questions. Here's the first practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answer. So in this question we have the ester ethyl ethanoate, which has an initial concentration of 1 mole per decimeter cubed, and it reacts with water at the same initial concentration and is allowed to reach equilibrium, and the equilibrium mixture was analysed and found to contain ethanoic acid at a concentration of 0.3 moles per decimeter cubed. We're asked to calculate the value of Kc. So once again I put in the initial concentrations. So we have an initial concentration of the ester of 1 mole per decimeter cubed, and of water 1 mole per decimeter cubed, and 0 of my 2 products. So if I represent the number of moles that react with X, the concentration at equilibrium of the ester would be 1 minus X, and the concentration of water would be 1 minus X. And it's 1 minus X rather than 1 minus 2X because there's 1 mole of the ester and 1 mole of water in the equation. So if X represents the number of moles that react, we'll have X moles of ethanoic acid and X moles of ethanol forming at equilibrium. Now they tell you in the question that the concentration of ethanoic acid is 0.3 moles per decimeter cubed at equilibrium, so therefore I can conclude that X is equal to 0.3. So therefore all I do is work out now the concentrations at equilibrium using the fact that X is equal to 0.3. So the concentration of the ester will be 1 minus 0.3, which will be 0.7 moles per decimeter cubed. The concentration of water will also be 0.7 moles per decimeter cubed. And as the concentration of acid and alcohol is X, that will be 0.3 moles per decimeter cubed for each. So now I have the equilibrium concentrations of the ester, water, the carboxylic acid and the alcohol. I can write an expression for Kc. Kc is equal to the concentration of ethanoic acid times the concentration of ethanol divided by the concentration of ethyl ethanoate times the concentration of water. And I have all these concentrations now. So I can put these into the equation. So it will be 0.3 times 0.3 divided by 0.7 times 0.7. And this will give me a value for Kc. Now if I put these numbers into the calculator, it comes out to be 0.184. Now I have to work out what the units will be. Now I have 2 concentration terms on the top and I have 2 concentration terms on the bottom. So we have moles per decimeter cubed times moles per decimeter cubed divided by moles per decimeter cubed times moles per decimeter cubed. Therefore these cancel out and we'll have no units for Kc here. Now it's important that we write in no units rather than just leaving it blank. So here's our second practice question. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answer. Now for question 2, we have Fe3 plus reacting with SCN minus to form FeSCN2 plus. And you're asked to work out the value of Kc in the following system. So once again, I'm going to write down the initial concentrations. So Fe3 plus has an initial concentration of 0.2 moles per decimeter cubed. And SCN minus also has an initial concentration of 0.2 moles per decimeter cubed. And at the start, we have 0 for the concentration of products here. Now at equilibrium, the concentration of Fe3 plus can be represented by 0.2 minus X, if we let X be the number of moles that react. And once again, it's X here because there's 1 mole of Fe3 plus in the equation. Now in the equation, there's also 1 mole of SCN minus, so the equilibrium concentration will be 0.2 minus X for SCN minus, and the concentration at equilibrium for FeSCN2 plus will be X because there's 1 mole of that in the equation. Now they give you the value of X in the question as 0.15 moles per decimeter cubed because that's the concentration of FeSCN2 plus. So I just substitute in this value to work out the different equilibrium concentrations. So for Fe3 plus it'll be 0.2 minus 0.15, which will be 0.05 moles per decimeter cubed. It'll be the same concentration for SCN minus 0.2 minus 0.15. And for the concentration of FeSCN2 plus, it will be 0.15 moles per decimeter cubed because that was given to you in the question. So now to work out Kc, I substitute in these values. So Kc is equal to the concentration of FeSCN2 plus over the concentration of Fe3 plus times the concentration of SCN minus. So if we put these values into the expression, we can have a value for Kc. So we have 0.15 divided by 0.05 times 0.05. So 0.15 divided by 0.05 times 0.05 is equal to 0.15 divided by 2.5 times 10 to the minus 3. And that gives you a value of 60 for Kc. Now we also have to work out the units. So we have moles per decimeter cubed on the top divided by moles per decimeter cubed times moles per decimeter cubed. Now we can cancel out moles per decimeter cubed on the top and the bottom here, which leaves me with units of 1 divided by moles per decimeter cubed, which therefore is equal to moles to the minus 1 dm to the 3. And that will be the units for Kc. So my answer is 60 and my units is moles to the minus 1 dm to the 3. So here's our next practice question, and this is slightly different because instead of giving you initial concentrations and equilibrium concentrations, they've given you initial moles and the equilibrium amount of moles. They've also given you a volume in decimeters cubed. So you are able, once you work out the moles of this at equilibrium, to work out the concentration values. Because remember, moles divided by dm cubed gives you concentration, because concentration is moles per decimeter cubed. So read for the question, pause the video, have a go at it, and then we'll go for the answer. Now in this question we have B reacting with C to form A, and they tell you the initial number of moles of B and C. So we know that there's 0.5 moles of B and 0.3 moles of C, and we know that there's a volume of 10 dm cubed here, which I'm going to use later. So I'm going to write in the initial number of moles here. So we have 0.5 moles of B and 0.3 moles of C, and we have 0 of A at the start. There's no A formed. Now at equilibrium, the number of moles will be 0.5 minus X, because there's 1 mole of B in the chemical equation. It'll be 0.3 minus X, once again, because there's 1 mole of C in the chemical equation. And A will have an equilibrium number of moles equal to X, because there's 1 mole of A in the equation. Now they tell you that A is equal to 0.1 moles at equilibrium. So therefore, if I know that, I know the value of X, which is equal to 0.1, and I can work out the moles at equilibrium of B and C, because it would be simply 0.5 minus 0.1, which is 0.4, and 0.3 minus 0.1, which is 0.2, and I know the number of moles of A present at equilibrium as it's 0.1. Now remember, Kc is an expression which has the products concentrations over the reactants concentrations. So I need to convert the number of moles to concentration. So to convert moles to concentration, I divide by the volume in dm cubed. Now the volume in dm cubed is 10 dm cubed. So to work out the concentration of B, I do moles divided by the volume in dm cubed, which would be 0.4 divided by 10, which is 0.04 moles per decimeter cubed. To work out the concentration of C, I do 0.2 divided by 10, which is 0.02 moles per decimeter cubed. And to work out A, I do 0.1 divided by 10, which gives me a concentration of 0.01 moles per decimeter cubed. Now Kc is equal to the concentration of A divided by the concentration of B times the concentration of C. So I just put these values into the expression. So I have 0.01 divided by 0.04 times 0.02. Now if I put these values into the calculator, I get a value for Kc equal to 12.5. Now to work out the units, I just substitute in the units of concentration here. So I have moles per decimeter cubed divided by moles per decimeter cubed times moles per decimeter cubed. So I have moles per decimeter cubed over moles per decimeter cubed squared. So if I cancel out the concentration terms on the top and the bottom, I get units equal to 1 over moles per decimeter cubed, which can be simplified as moles to the minus 1 dm to the 3. So my final answer is 12.5 moles to the minus 1 dm to the 3. So here's our final practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answer. So once again for this question, we're given the number of moles at the start, and we're given an equilibrium number of moles. So I know there's 4 moles of A at the start. I know that this was placed in a 20 dm cubed container. So I do have a volume here, so I can work out concentration later. So I'm going to write down the initial number of moles as 4, and my initial number of moles of B will be 0. And then I'm going to write down an equilibrium number of moles, which is 4 minus X, because I've got 1 mole of A in the equation. So that's why it's 4 minus 1x. And I have 2x to represent the number of moles of B at equilibrium, because there's 2 moles of B in the equation. Now the question tells me that at equilibrium the number of moles of A is 1.50. Now I know that the number of moles of A at equilibrium is 4 minus x. Now that's equal to 1.50. So if I rearrange this, I can get the value of x, and x is equal to 2.50. Now if I know the value of x is 2.50 moles, I now know that I have 1.50 moles of A at equilibrium and 2 times 2.50 moles of B, because B is equal to 2x. So I now have the moles of B, 5 moles, and the moles of A, 1.50 moles. Now, I now need to work out the concentrations of each at equilibrium, because Kc is equal to the concentration of B raised to the power 2 divided by the concentration of A. Now, to work out the equilibrium concentrations of A and B, I simply do moles divided by the volume in dm cubed. Now, the volume in dm cubed is 20, so the concentration of A in moles per decimeter cubed will be 1.50 over 20, and the equilibrium concentration of B will be 5 divided by 20. So that will give me equilibrium concentrations equal to 0.075 moles per decimeter cubed for A and 0.25 moles per decimeter cubed for B. So now that I have the equilibrium concentrations of A and B, I can substitute these values into my expression for Kc. So Kc will be equal to 0.25 squared over 0.075, and this will give me a value of Kc equal to 0.83. Now, the last thing I need to do is work out the units. So we have two concentration terms on the top and one on the bottom. So we have moles per decimeter cubed times moles per decimeter cubed on the top divided by moles per decimeter cubed on the bottom. So that gives me units of moles per decimeter cubed. So my final answer is 0.83 moles per decimeter cubed. So that concludes this video lesson. So after watching this video, you should now have an improved understanding of the concept of the equilibrium constant Kc and what the values of this constant tell us about the position of an equilibrium. And you should also be able to calculate Kc from given equilibrium concentrations and be able to work out the units for this constant. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.